Hello everyone and welcome to my video on using machine learning for stock market prediction. Unfortunately, this is not magic, and the big picture is that predicting stock prices is extremely difficult. At an intraday level, it is extremely hard to beat the baseline of flipping a coin when you want to predict if the direction of the price change will be up or down, if the stock will go up or down. It is also extremely hard to predict the baseline of the next stock price will be the current stock price, meaning that the return is zero. So basically, that the stock stays at the same level. Those are some baselines that are extremely hard to beat. And whenever you're running models, you want to always compare your models to that baseline. At the same time, if you beat the baseline by a wide variety, or wide margin, it probably means you're overfitting. So like you definitely want to beat the hard to beat baseline, but you can't overbeat it, because if you're overbeating it, chances are you have some leakage or some problem. So in this video, first I'm going to talk about those specific evaluation metrics that I spoke about when comparing to the baseline, and just showing you guys basically what we need to beat. And also I'm going to talk about like an end-to-end walkthrough. We're going to talk about feature extraction, model training, and model evaluation. For feature extraction, we're going to be using simple technical indicator features from the Pandas TA library. Of course, if you these are not the best features. The best features would use some crazy things like satellite images, social media posts, Google Trends, all these things, number of shopping carts, weather, all that good stuff. Other correlation with assets, bond yields, all these things. But just for simplicity, we're going to just talk about technical indicator features. And then I'm going to show you how to train some of the most popular models like decision trees, random forests, Catboosts, neural networks, LSTMs. And we're going to do 5-minute predictions, and we're going to evaluate and compare to the baselines we spoke about above. So the main tasks for supervised learning are, in this case, will be binary classification, which would be predicting if the stock will go up or down. And as I said previously, it is extremely hard to beat the baseline of randomly flipping a coin. For regression, we're going to predict either simple returns, which is the change of the next stock price minus today's stock price over today's stock price, or the percent change in the stock price, or log returns. Log returns are honestly a lot better, because it's if the stock doubles and then halves, it goes back to the same value, meaning if it goes up 100% and down 100%, it goes back to the same value, so it's additive. But for simplicity in this video, we're just going to focus on simple returns, which is this formula here. It means like the next stock price minus the current stock price over the current stock price. These are still better than predicting the actual stock prices, because you don't have to worry about scale. But again, it's very challenging to beat the baseline that this return will be zero, meaning that the stock price did not change. Okay, so let's talk for a second about why predicting stock price is extremely difficult with machine learning or with anything. So the market is extremely efficient. Everything is priced in. Any pattern is priced in. Any news is priced in, or at least very fast priced in. So like the market efficiency is very hard a challenge. And honestly, if the market is perfectly efficient, like the efficient market hypothesis, you can't do any prediction, because everything's already in the stock price. Of course, that is not true. And pretty much the goal of machine learning for stock market prediction is to find these inefficiencies. There's extremely high noise to signal ratio. Basically, there's so many participants, so many people go in and out for a variety of reasons. There's so much noise. You really don't know, like, okay, if Tesla's selling off, is it really because Tesla's bad, or is it because people want to change to a different stock and their capital is tied up? You don't know like the reasons. Why is one fund selling? Why is one fund buying? There's so much noise, and everything is not stationary. Patterns today are not the same as patterns tomorrow, and that sort of thing. And that's why also overfitting is extremely big deal. It's so easy to find like some random mix of technical indicators that gives you a good performance, but you're probably overfitting, and that won't hold in the future. There's so many unquantifiable factors, like I don't know, like terrorist attacks, God forbid, all these things, like all these random things that you just don't know, and they influence the stock prices, and you can't really measure them and quantify them. Also, I wanted to say that like, um, and usually ML algorithms do well with like IID data or are assumed to be IID, but like in finance, that's rarely the case. Anyways, so before I get into more detail and start this video, I just want to say that I have a weekly series of machine learning applied to finance. So please subscribe to my channel. I'll have one video a week of these topics in much more detail, much more of the nuances of ML applied to finance. I will have in the description a playlist of this series, and please in the comments write suggest topics, that sort of thing. I'll go in much more in depth into intricacies. So if you find this video useful, please subscribe, and you'll see the weekly ML video applied to finance. Okay, so so let's get started. At first, I want to talk about binary classification before we do any modeling and any of that sort of thing. And namely, I want to first talk about some of the loss functions and evaluation metrics. So of course, usually in machine learning, you fit an algorithm by trying to minimize some loss function, and then you evaluate an algorithm, right? So the loss function for most binary classification is usually log loss or binary cross entropy. So that's this function here. So it's like you have negative 1 over n times the sum of yi times log pi plus 1 minus yi times log 1 minus pi. So the intuition is the accuracy of your classifier, the closer. So yi is the label. It's either 0 for stock going down or 1 for stock going up. And pi is the probability of the stock going up given by your model. So the idea is you want to penalize mistakes and you want to weight it by the confidence of your predictions. So let me give you guys like the extreme case. So let's assume the model, the label is 1, meaning the stock goes up. So we want our model to be very confident. So we want, since we're trying to minimize this log loss quantity, minimize this log loss quantity, right? So let's talk about the two cases. So like, if we ignore the sum, we'll just focus on one point. If the label is 1, meaning the stock goes up, the log probability, the higher the probability, if the probability at the extreme is 1, then it'll be 1 times log of 1, which is 0. And here it's 1 minus 1 is 0. It's irrelevant. So it's 0. So the log loss is 0. At the other extreme is when the probability is low, meaning it's a bad prediction. So the log of almost 0 is negative infinity. Negative infinity times minus is plus infinity. So that's bad. So in general, the higher the probability when you have a positive label, the lower the log loss. And similarly, if you have a negative label, meaning 1 minus 0 is 1, the lower the probability, the lower the log loss. So this is basically the #1 loss function used to fit every model, but it is very useful for us in having this baseline of whether the whether we can beat random guessing. So what is a baseline for this? So assuming that we have the same amount, meaning same amount of times the stock goes up or down, meaning we have a balanced data set, we should beat the baseline of negative 0.6, sorry, this should be, we should beat the baseline of 0.6931. So why is this number so magical? So if you think about it this way, if you were to say half of these yi's are 0, half are 1, so this will be a half, and then this will be a half because half are 0, half are 1. And then log pi will also be a half because you're randomly guessing. So 1/2 times log of a half, because this pi is a half, and log of 1 minus a half is also log of a half. So it'll be basically a half times log of a half plus a half times log of a half is log of a half, and then it'll be n, and then negative 1 over n times n, it'll be negative log of a half, and then log of a half is 0.6931, so negative of that is 0.6931. So this is the baseline we want to beat for random guessing, and I'll show you it's not easy. And if you do beat it by a substantial amount, you probably have a mistake in your model. Okay, so just real quick, there's also the confusion matrix. Like there's the true positives, number of times you predict the stock will go up when it actually is up, when it is actually up. True negatives is number of times you predict the stock will go down when it's actually down. False positives is the number of times you predict the stock will go up, but it's actually down. And false negatives, it's the number of times you predict the stock will go down, but it's up. And there's also these metrics of like precision recall. Precision is like, let's say if you're only cared about like making buy trades, it's like the number of times your model predicts a buy and you are correct about it. And recall is out of all the good buying opportunities, what percent of them that you found. We're not going to worry too much about these, maybe just the confusion matrix, just to show you guys, because like it's a matrix of all these 4 quantities, just to show you guys like how close it is to random guessing. But there's another metric that people use for like binary classification. It's the area under the ROC curve. So the ROC curve, what it does is, so our models have a probability threshold, and we can, it gives us like, we have a score between 0 and 1 for how confident we are in our prediction. So at each score, we can say like, okay, above 0.7 buy, above 0.65 buy. So each one of these scores gives you another value in this curve. So when you like do all the scores one by one, you get like this entire curve. And the area under the curve is some metric for how the model is doing. The better the area under the curve, the better the model is doing. Random guessing, the area under the curve is 50%, so we want to beat that 50% thing. There's also, of course, accuracy and that sort of thing, and balanced accuracy. Those, of course, like the random model would be 50%. But yeah, like the goal here is just basically to show you guys just how hard machine learning is for finance. So before we get started with the actual algorithms, let's talk about, let's just build some sort of classification report. And this classification report is going to use Sckit-Learn. So this will be kind of like how we're going to evaluate our models, right? What we're going to have is, we're going to just say like, okay, our model, when we predict it on the test set, will return like probabilities or confidence scores. And we have their actual labels of stock going up or down. We're going to print the confusion matrix, an accuracy score, balanced accuracy, which basically will make the number of times the stock goes up or down is balanced. And then there's a classification report, which gives you details on false positive, true positive. I just added this for completeness, but like there's also the area under the curve and the log loss, or the binary cross entropy. The key is the last two, and because those are the two we really want to compare to the random guessing baseline. So this is the classification report. This is using pure Sckit-Learn. So I imported these at the beginning. I did from Sckit-Learn.metrics import all these things. So anyways, that's just that. Also, of course, Sckit-Learn is also called Sckit-Learn. So yeah. Okay, so this is going to be used to evaluate our models later on. Okay, so now we're going to use 5-minute data. I have a dataset CSV file. I have other videos that show you how to get the CSV file, especially if you're using interactive brokers. If not, maybe reach out to me. I'll show you. But like we're gonna read from CSV using pandas, and then since I have outside regular trading hour data, I'm gonna do between time to get regular trading hour data. And because I'm using 5-minute bars, the last interval is 59.55. The reason for this is, I mean, you don't have to do this, but like outside regular trading hours behaves very differently. Of course, I have other videos that don't even use time bars because time bars are very non-stationary and non-IID. I usually use dollar bars personally, but I have other videos about that. So look at my channel and you can see them. So, okay. So now let's create the label. Okay, so the label is, so what we can do for the label is we can do something like this. We can do df label equals np.sign. Sign df the future closing price close.shift -1. The shift, of course, moves this back to here. So that's like the future price minus df close dot shift. And of course, if it's up or down, df close, if it's up or down, it'll tell us with the sign. So we see df dot label dot value counts, but you'll see this is not binary because there's some that that it didn't change. But like just for simplicity of this video, I'm gonna just ignore this 0 for now. But I don't want to actually delete it because it'll kind of make the technical indicators not be true. And then so what I'm gonna do actually is I'm gonna do something like very simply if df label equals df dot close minus dot shift -1, it means the next price. If it's greater than df close the current price, and then I do as type int, meaning if it's equal, I'm just gonna set it to like the -1 label, just for simplicity. So now you can look at the value counts also and see if it works. Okay, great. So this is the label for binary classification. So now I'm going to show you how to get features. I'm going to use Pandas TA to get the technical analysis features. I have a video on Pandas TA. I'll put it in the description. I also have a video on TAlib and installing TAlib. Those are similar libraries, probably much more, I think they're much more robust. But for Pandas TA, you basically kind of write the indicators here. So I purposely have an indicator that's not good. There's one indicator that actually does leakage. It's called DPO. So the DPO indicator does leakage, and that's a huge problem. And you'll see it come up when we start fitting the models. So basically, and then I calculate like a few other things. Just to remind you guys is like you have like basically a dictionary of your technical indicators. You do this TA strategy, you put your indicator list, and then it gets you the indicators. I added a few feature extraction things that I created, like the autocorrelation, that sort of thing. And then so you get the data frame with the features once you apply this method. Look at all these beautiful features. Okay, so now like with most machine learning, we have to split the data into two, train and test. There's train, test, val, there's cross-validation, there's a million things. That's where when you have to subscribe to my videos, and we'll be talking about that in much more rigor in future videos. But just for simplicity, let's assume we're going to just split our data set. We'll do like 60% for training, 40% for testing. The first 60% is training, and the second 40% is testing. So I do that here. I guess I didn't run this, so I don't have this df with features. So now, okay, it might take a bit of time. So yeah, this is just the, I did have DF with features. That's really weird. Yeah, it's really weird. I thought I had it. Let me restart for a second, and let's just run everything from start. Sorry about this. Uh, so I created this DF with features, right? And then I split it, and then why did it complain? So I basically split it 60% for training, next 60% for testing. Um, but we'll kind of not to waste time. For our algorithm, we want to define the features we want to use, so we'll define these features. And I purposely split it like this, where I have this list of features, and then I have this. Okay, it worked now. I have this list of features, but then I made it like this. I added this DPO 20 here because I know DPO 20 is screwed up. Okay, because it actually leaks. It looks ahead of time. So the DPO 20 is very bad. So I just want to show you guys something. So like, okay, this is the critical note I wanted to say is like, if you have good accuracy, like 55 or 60%, especially at intraday level, it means you have some sort of leakage. If you can predict 55 or 60%, you're going to be a really rich person. So that's just not possible. Unless, of course, we're of course making the assumption that our trades do not impact the actual stock prices. But for small traders like me and you, maybe, that's a reasonable assumption. But like, there's a data leak in DPO. If you click this link, you see in the GitHub, it talks about like data link for DPO indicator. So you'll see it here. Okay, so let's first talk about, let's fit the simplest model, decision tree. So decision tree, and this is also great for debugging because right away you'll see the problem. So let's just, for the sake of argument, do max depth equals 4. Since decision tree isn't really a good algorithm, I mean, it's a great algorithm, but it's not the most accurate algorithm on its own, because if the decision tree is too deep, it's overfitting. If it's too shallow, it's underfitting. It has like no in between kind of, but it's just good for for understanding things. So I do I define the decision tree. I fit the function. I do fit. I put the X, which is train feature calls, and then I put the Y, which is train label. So I'm fitting the model here. Oops, sorry. Okay, and let's plot the. First of all, before we plot anything, you know what? Let's just not have max depth for a second, just to show you guys. So I'm fitting the model, and then I remember we had the function of so we can first of all, we can make the predictions. We can do clf.predictproba, gives us the probability, and test feature calls. But we want the second thing, because the first thing is predicting the 0 label, the second thing is predicting the 1 label, and we get the probs that look like this. It's 0, 1 just because it's a decision tree fit all the way. It won't be 0, 1. Just give me a second, I'll show you guys. And then we can do our get classification report. Get classification report, test.label, and probs. So we get our classification report. So wow, our AUC is 54%. Our log loss is a mess. Why is this? Let me show you guys in a second. But like, the accuracy is so high and stuff. Let me just show you guys in a second. Let's just do max depth equals 4 for a second, because now we get more reasonable values. The reason this log loss got messed up is because like you get a lot of one values and stuff like that. But let's not get into that just for a second. But like, the key is, and by the way, the log loss is so messed up. Was so messed up that it was like way worse than random guessing in that example. But now you see something else. You see that the log loss here is actually way better than random guessing. It's 64%, and your AUC is 67%, and your accuracy is 63%. This is so good. Is it too good to be true? Well, we can plot the tree and see. And as you see it, look, right away we notice something. We see this DPO indicator. First of all, I don't even know what the DPO indicator is. I'm not a technical analysis expert. DPO indicator. What is this? Detrended price oscillation. It measures the distance between peaks and troughs in price cycles. I don't even know what this indicator is, honestly. But look, it's basically using this as like a magic indicator. So like maybe that's a hint that something might be wrong. And sorry, I wasn't explaining it so well. The fitting the tree all the way got you a log loss of like a huge number. It showed that the model was bad because it way overfit. But like when we do max depth is 4, the log loss is too good to be true, and the accuracy is too good to be true. So let's just keep showing you guys this for a second, and then we're gonna remove this feature for something more reasonable. So let's do random forest. So all these are from Sckit-Learn pretty much. So we can do classifier equals random forest classifier. We can also do this class weight equals balanced to deal with the fact that our classes might be in balance, and then we fit the model like previously. We do train feature calls, train label, and then once we do that, we can do the classification report we created as above. Remember we did this thing. So this takes a second longer. Random forest while we're waiting is my favorite algorithm, and I'll do a video about it, but basically it's like a lot of these decision trees each fit with a different random subset of your data with sampling with replacement, so bootstrap sample, and also you randomly select a subset of your features. That helps deal with correlation. It does take a bit longer to fit, even though actually this is the most parallelizable algorithm in the world, but I'm just kind of like naively doing it on my computer with the default settings. So let's wait a little bit, and then we're gonna plot this. We're gonna look at this classification report, and then after, by the way, this will also okay. If it just finished, so we're gonna do this classification report, and wow, again, accuracy super high, AUC super high, log loss super high, too good to be true. Another way you can see that it might be something's off is if you can look at feature importance. So there's a thing called CLF.feature importance. It gives you the feature importance. We can visualize this as a data frame by doing PD.dataFrame, and then we can do something like feature calls, and then we can do score CLF.feature importance is. And then we can do sort values, use score ascending equals false. Did I make a mistake? Probably. Don't know why my computer is so slow. Maybe I have. So look, this DPO thing gets like such a high value. So maybe something is wrong. So I think you guys get the picture. Just for the sake of completeness, like I can also let me do Catboost for a second. So Catboost is like literally the best algorithm for any sort of thing when you don't know anything and you don't want to do anything. So I don't know. I'm just gonna throw in a parameter or two. Learning rate equals 0.001. Random seed. I'll show you later why random seed is useful. It basically it's a different randomization each time. You can do the class weights equals balanced by using auto class weights equals balanced. We'll do a deep dive in random Catboost. It's my second favorite algorithm, probably my favorite now. And then similarly, you fit it, but like just ignore some of these things. Will give me some evaluation while I'm at it. So like it's fitting the model. It also I set the test set to the validation set. Obviously, you shouldn't do this in real life, but you see like it's like almost perfect. The validation set going down. My learning rate is too small. It's too small here. Um, let's make the learning rate like this, and look at how crazy good this is. It goes to like uh, the way less than the 0.693 baseline of log loss. Again, we can look at the feature importance. We can literally copy this code, and you're gonna see that the DPO thing is an issue. The DPO thing is popping up way more, and of course we had the our previous thing where we did the classification report, right? So we had this thing. And of course, it's too good to be true. This is 70% AUC. So let's remove the feature we know is messed up, and let's see how things change. So let's remove this feature. And when you remove this feature, now you're, wow, that's still pretty good AUC. But look, the log loss is 0.695, worse than random guessing. The accuracy and balance accuracy is a little bit better than random guessing, but the log loss is worse. So it's not, it's kind of like random guessing. Maybe by chance we did better. But now it makes more sense. You look at the log returns, stuff like that. And then when you fit the random forest, of course, you'll see something. Here I'm going to already set the learning rate to a little bit less for the Catboost, just to, because I know, I'll keep it like this. See, the random forest like naively is taking forever. Let's make it a little bit faster. This is just because I want big picture for you guys to get the thing. I'll do like max depth equals like 8 or something. And yeah, of course, if some of these specific algorithms are a lot more interesting to you guys, we'll do a deep dive into them. But like, so like the random forest, now that we've removed that cheating feature, the DPO, the leaking feature, let's see how the random forest is doing. Okay, the random forest, see, it's still worse than random guessing, the log loss, 0.6933. We need 0.6931. We can look at the feature importance. Now it makes more sense. You don't have like one feature dominating everything. So now we can do the Catboost. And now you see Catboost is obviously the best algorithm. It's a little bit better than random guessing, but like it's overfitting pretty quick. After 75 iterations, the test set doesn't really go down. So I'm already cheating if I'm going to run it again, but let me run it again with a different learning rate. Why am I cheating? Because like if you keep like trying to optimize your validation or test set, you're like kind of like you're cheating. You're not talking about like the number of trials to get there. And Lopez de Prado's book speaks about that a lot, Advances in Financial Machine Learning, and we'll talk about that a lot. But like, look, anyways, this specific example, we do better than random guessing. We do get like a log loss of like 0.69 something. But I want to say something interesting with Catboost. I know specifically for this example, it's not going to matter too much. But like if you change the random seed, the randomization, sometimes you can get completely different values. So it's always, you always want to like play around with a few random seeds just to make sure that like you don't have, you're not by luck getting a better value. So like here, it definitely is a little bit better than randomly guessing, at least on this data set. And then we can look, of course, at the classification report and that sort of thing. And the feature importance will make more sense. So I guess even this kind of overfit at some point after 670 iterations, right? But you see with the classification report, the accuracy, AUC is 51%. The log loss is 0.692, better than baseline of 0.6931. Accuracy, confusion matrix, a little bit better than random guessing. So this seems like more promising. You can look at feature importance. You see, it's reasonable. Not one thing is dominating too much. And just because we're doing this walkthrough, I want to also talk about like neural networks, because there's been like trillions of videos online about neural networks and LSTMs predicting stock prices, and they're pretty much all cheating. So let's just do like a simple model from Keras. Like we're gonna do two types. So we're gonna do just basically like one layer multi-layer perceptron where you have a dense ReLU layer and then a sigmoid layer. And just for neural networks, unlike Catboost or tree models, we do need to standardize our data, so we can do like scalar equals standard scalar. This is of course from Sckit-Learn, and then we have to fit it on the training set only. So we do train x equals scalar dot fit transform train x, and then we can do test x equals scalar dot transform test x. Test feature calls, and then this is train feature calls. Okay, so you want to make your classes balanced, but there isn't a helper like the balance thing like we saw above with Catboost random forest. So you have to do it on your own. So you can do something like this if you have test. Your label will be train label, and then value counts gives you the value counts. You can do normalize equals true to get the proportions. You can do 1 over this to get the inverse proportions, and then you can do the dot dict method to dict because you need it as a dictionary, and then we can call this class weights. Okay, so we get these class weights, and then so for Keras, you have an optimizer. You compile your model, give it a loss function, some metrics you want to see, and then you fit the model. So let's show that. Basically, I'm rushing through this. This is kind of just to show you guys it's not magic, but like just to show you guys, like a lot of the videos on LSTMs and stuff were like so perfect, but in reality it's not perfect. And then when this is done, we're gonna run the classification report. I'm printing out after each epoch or pass through the data, like the validation binary cross entropy or log loss, whatever you want to call it, same thing. And it's also spitting out the training thing. This could probably go on for more iterations. So you know what? Maybe we should actually let's keep it going just a little bit. But like the point is, look at the validation loss. We already see it's struggling to get to 0.6931. It's worse than random guessing. Of course, with using deep learning, you're much more susceptible to like outliers and that sort of thing. So you have to be very careful. But like just to do the classification report, we see that our AUC is pretty good, 0.51, but our log loss is worse than random guessing. So that's something to consider. And let's talk about RNNs like LSTMs. There were so many videos when LSTM came out on like predicting stock prices. Literally all of them were not true. LSTMs are basically like a sequential model where you have like some sort of like history and you predict the next price. Like it's like a sequence model. So you would need like a get sequence function. So it'll give you like sequence length times number of features. So previously we just had number of features as our input. Each label had number of features and a label. And now we have number of features and sequence length in a label. So this helper function creates sequences, gives you a sequence. You see like train X sequence. You'll see if you look at the shape of it, you'll see that it's like it's basically has 12 by 19 because I set the sequence length to 12. Why 12? Because if I'm using 5-minute data, 12 is like an hour. Maybe I can use 78 for 1 day. If you do 6.5 hours in the trading. But anyways, this is just to show you guys. So big picture is you're fitting your your sequences are the 12 by 19, and you have 3,000 of these. Just to show you guys, I'm gonna spare you guys the detail. You can fit the model. And you know what's crazy is a lot of things, they don't even use these feature columns. They actually use the actual just open, high, low, close volume as their features. And that's even worse, honestly. You can use that. I'll show you maybe in the next part on regression doing that. But anyways, yeah, LSTMs is not gonna give you, it's not magic. You know, you're not gonna magically have perfect results, right? And then when this is done, we're gonna show you the classification report. So yeah, so the deal is we want this loss function to go down. Okay, while this is running, we're gonna next thing we're gonna talk about is regression, right? So let's let this run a little bit, and then I'm gonna talk about regression. So for regression, the difference is now we're gonna focus on predicting simple returns, which is like in our case it'll be the like next closing price minus the current closing price over the current closing price. For regression, the most common loss function is mean squared error, where it's you're basically trying to minimize the sum of squared errors between your prediction, the y hat you're predicting, and the actual. So that's what you're trying to optimize. But like to report metrics, you can report maybe root mean squared error, which is like the square root of this. Just because this gives you like a scale of real life, the mean squared error is like a square root of real life. Root mean squared error is basically square root of that. There's also mean absolute error, where you're trying to minimize the absolute error between yi, your prediction, and the actual. This is much more robust because if you have the squared error, you have one bad predictions or outliers really influence things a lot more, but absolute value influences less. There's R squared, which measures the goodness of fit. Let's not talk about it too much. I think what's more interesting is there's a thing called information coefficient, which we also won't talk about much, but basically this is used a lot. It's to measure the correlation between your predicted returns and actual returns. So we're going to actually speak about that. We're not going to speak about that because for benchmarking, it's undefined for the zero return thing because the correlation has a standard deviation in it, and zero return benchmark standard deviation is 0, so it'll be like 0 in the denominator, so undefined. But like in general, this is a good thing to do to compare models, the information coefficient, which is the correlation between the predicted and actual returns. Let's go back to our LSTM because we're done. As you see, the validation loss never got to what we wanted. Never got to beating random guessing of 0.6931. But you see, like the AUC is pretty good. So like the thing about log loss is it has the confidence of our predictions, something that's meaningful. So like it's not the only metric, but like there does seem to be some predictive value, but like you gotta be very careful. This accuracy seems too good to be true. This seems by luck it's accurate like this. I probably have another error in my model. The accuracy cannot be too much. It cannot be like this. So you have to keep scrutinizing your model, keep seeing what you might have done wrong, what you might have cheated on. Okay, so anyways, that's classification. So for the regression, we're going to continue about talking about it. So the benchmark we want to beat is predict that the return is going to be 0. So I'm going to show you guys like just how hard it is to beat that. So I spoke about the main metrics, the the mean squared error, the mean absolute error. I think those are the two most important things we can compare. So let's get started. So like here, I'm not going to get into the details. Similar to the other video, I'll have a regression report, which will have like the errors of the model, the true minus predicted, mean squared error, root mean squared error, mean absolute error, and R squared. Then we're going to compare it to baseline. We're going to have a baseline of predicting the return is 0. But here we're going to calculate returns. we're going to use ordinary returns. Log returns are a lot better. You should use log returns, but just for simplicity, we'll do ordinary returns, which is the percent change. Basically, the next closing price minus current over current. That's your label. We're going to use pandas TA to extract features. Like in the other video, we're going to split into train test, define the feature columns to use. Let me show you guys the decision tree first. We'll wait for it to run. Where are we stuck? So look at the decision tree. Our mean squared error is this. It's worse than the baseline. It's higher than the baseline. The mean absolute error is also higher than the baseline. So yeah, it's worse than those two things already. R squared is higher, is worse because you want R squared close to 1, but you have a negative R squared. So even R squared is worse. It's just worse than the predicting the constant value. So now let's do random forest. And let's see if it's better than random guessing. This takes a little bit longer. You know what's funny is like random forest is so parallelizable. You can run one model in China, one in the US, one in Japan, one in Korea, and then they can combine it together because like it's not a sequential model at all. But because I'm not using any parallelization, it's taking forever. And then the last model would be Catboost, and then the neural networks. And this is just honestly to show you guys that it's hard to beat just not predicting that the stock will not change. And also shows you, as you saw previously, is that classification is a little bit easier. And just one note while this is running is I did not use the DPO feature. I used just kind of legit features. And by the way, in my previous video, the reason the accuracy of 51% was maybe so good might have been because in other videos I kind of like, in other calculations I kind of, I might have did some feature selection, so I might have further biased things. So anyways, this is running. Let's wait. Let's try to be patient. Okay, so look. So 1.62, worst mean squared error, worst mean absolute error. The R squared is R squared seems to be better in this case actually. So R squared we beat, but like the baseline, but like we were worse on the baseline and everything else. Catboost, of course, is the best model out of the box. If this loses, we have no chance. So, oh, yay, Catboost beat it a little bit. So moral of the story is Catboost is the best model out of the box by far. It beat the mean squared error. It beat the mean absolute error. No, 0.023566. I think this beat it a little bit. So Catboost out of the box beat it a little bit. So the moral of the story is out of the box, Catboost is the best. Now we're going to do the neural network. The only difference here is like, I didn't show you guys. In the previous video, we had activation as sigmoid, right? Because that's predicting 0, 1. Here, the activation is actually going to be at the end linear. I guess I added 2 layers just for the hell of it. But yeah, you see here, you see that its mean squared error is higher. Mean absolute error is also higher. So this is worse than the baseline. And now I'm running, I have a LSTM, similar example, and LSTM is worse. So I just wanted to say that some people have done prediction on using like just open, high, low, close volume features. So I was saying is, okay, you could add these features and then you can still do it, and you can still get a worse answer a lot of times. And you can also use just open, high, low, close volume to get a worse answer. Anyways, this was just supposed to be a walkthrough and show you guys like ML is not magic when applied to stock market prediction like a lot of videos say. If you enjoyed this video, please like and subscribe. I have a weekly videos on ML for finance. Also, I'll have a lot of videos on practical algo trading, especially with interactive brokers. And I've been Sync. Hope you enjoyed and have a great weekend. Thank you.